Hello, everyone, and welcome to Clara's newest webinar, How to Deploy a Successful Performance Audit. Thank you for coming. In today's presentation, we'll start with some introductions, introducing myself and my colleague, and then we will talk about what a performance audit is and what goes into it, the pitfalls of not doing performance audits. Then we'll break down the critical metrics that you want to look at during an audit and how you can use that information. Then we'll talk about the ongoing process of auditing and how you apply that to plan future growth and maintain the health of your systems. Then we'll talk about Clara's offerings in this area, and then we'll take some questions and go from there. So to start, I'll introduce myself. My name's Alan Jude. I'm a co-founder at Clara and the ZFS engineering manager, and I'm joined today by...
Hi, I'm Mateusz Piotrowski. I'm a senior systems engineer at Clara. I specialize in tracing and performance engineering. Thank you for joining us.
Yeah, so to start, we're going to talk a little bit about what a performance audit is and what exactly goes into it.
All right, thank you, Alan. So we have 5 key items that we need for a successful audit to happen. So the first one is the observed performance. This is the current performance of your application, of your system. This is something that's happening at the very moment in your setup. Then we also want to identify the expected performance, so what the system is capable of. And then we have 2 very similar items, but they're slightly different. So there is system tuning and workload optimization. The system tuning focuses on your system, it's not your application. This is how we can tune the system to close the gap between the observed performance and expected performance. And then we have the workload optimization, which focuses on improving your application so that it uses the system in a more performant way. And the last item is the growth capabilities estimation. We can also call it usage projection. So this one tells us how we can plan our workload, how will the workload change in the future, whether we can absorb whether we have the capacity to absorb the changes, and if we have the plan to expand the system when needed. And with those 5 items in mind, let's move to the next slide.
Yep.
So this is what people usually know about their systems. They have some idea of the current performance they have. This is something they measure. And they also have this rough idea of suspected performance limits. So this is something people assume their systems are capable of, what it can offer in terms of performance, but there are very often no numbers to back it up. It's a rough area on the plot. It's nothing specific. It's often based on intuition and information people got from hardware manufacturers, but it doesn't take into account things like the characteristics of their workloads or the system configuration.
Yeah,
and then with an audit,
looking at this, you see, it looks like there's lots of room to grow here, and that the system's not going to run into any trouble. But then reality sets in.
Yeah, and with a performance audit, we can learn about different things about the performance of our system, right? So the first thing that we focus on over here is the current maximum performance. So this is what we currently can achieve with the setup that exists in the system, right? And very often this is not enough for the expected future demand. So based on the insights you may have about your expected growth of how your application is going to be used in some time, you can understand what's your expected future demand, and then realize that perhaps the current maximum performance is not enough. And that's when we start to...
The first part is that, as we saw in the first graph, most times people don't actually know what the current maximum performance is. They have some suspicion of, what it's supposed to be, but not what it actually is. And so they run into it a lot sooner than they expected. And then, yeah, like you see on the graph here, the expected future demand actually exceeds the current maximum performance, which means, the system won't actually be able to keep up.
Yeah, and that's when we start to benchmark the system as a whole. We try to simulate the workload maybe, just to understand what is the potential performance we can get out of the system. And ideally, we try to get as close to the system limits, but then the system limits is something that is very theoretical. This is something that the system is potentially capable of, but taking into consideration the workload and the configuration you need for your application to run, you can reach the potential performance, which is slightly lower than the system limits. And you can achieve all of that with workload optimization and system tuning. Yeah, that's how you can improve the performance of your system and prepare your system for future growth. So ultimately, once we have all those numbers like potential performance and the current maximum performance and so on, we can start to close the gap and move closer to the potential performance.
Yeah, getting the current maximum performance as close to the potential performance as possible. And that's all that extra performance that you didn't have before and you will have after your system's been optimized and tuned.
Right. So what are the outcomes of a performance audit? So first of all, we try to establish a baseline. So we measure the current performance and the system limits, and we start to understand what does it take to get to the potential performance. How does it compare to this metric? And then the second outcome is that we get the tuning and optimization. So we apply the system tuning and work optimization to the infrastructure, the system, and we try to get the most out of what exists in the system at the moment, right? So we try to achieve the peak performance of the system without adding any new hardware or expanding it in any way. The third outcome is that we can now start planning for expansion. So now that we understand the limits of our hardware and our system as a whole, we can start to create a plan for growth to stay ahead of demand. This is especially important for example, for hard drives or disks in general, because the lead time on new hardware nowadays is quite long, and receiving a replacement disk can take many months. So it's good to plan ahead when you need new hardware, right? When you're going to need new hardware. And then the last outcome are the quick wins, which can be described as expert recommendations to redeploy resources and make minor additions with outsized benefits. And we've prepared an example for you in the next slides to illustrate that.
Yeah, so we have a success story where we did exactly that. So we had a customer that has a backup application, and so their system was very busy with a metadata-heavy workload. Right? The backup application is comparing the files on the source system and the files on the backup and deciding which files on the backup are out of date in order to update them. But because it's a backup system, they optimized their system originally for storage capacity. They needed as much space as possible to have as many backups as possible. But this presented a problem that all these metadata operations, just figuring out which files actually need to be backed up, was consuming all the IOPS from their hard drives. And so that left no headroom for actual operations. So doing the backup was always slowed down by all the metadata operations. And that was because the application was comparing this metadata all the time. But we look at a workload optimization, there's not really a way to make a backup without knowing which files to back up. So we couldn't optimize it there. So instead, we looked for a quick win. By adding about 1% of the total pool size as SSDs, as the new ZFS metadata VDEV, we managed to move all of those IOPS for metadata off to the SSDs, which have a much higher capacity for IOPS than hard drives do. And so not only did we move all the reads of metadata off to the SSDs, freeing up those IOPS so they could be writes to the hard drives to ingest new backups, but it also meant the writes for those metadata also went to the SSD, had a much lower latency, and allowed us to have more of the writes to the hard drives be larger. And we'll talk about that more later on. But the result was very, very much improved times for backups, because you spend more of the time during the backup actually backing up data rather than spending most of that time just walking the directory trees and figuring out which files need to be backed up.
Yeah, and you may think, I don't need to know all those things about my storage. My storage systems are performing all right. And this may be true, but it also turns out that the storage audits are still rather important. So those audits bring you the understanding of your storage, of the performance of your storage system. So the thing is that storage is a contained resource. So it only takes one application change, one application is misbehaving to slow down your entire system. And this is not great. So it's good to have some knowledge about what how your system reacts to changes in your storage. And in order to avoid these kind of contentions, you must have the knowledge of your current performance, the expected future demand, and potential performance. So basically, in order to avoid those problems, you have to know how your storage is performing, how changes in applications and infrastructure are impacting it, and how much capacity you have left, right? So that you can plan for the future.
Yeah, like you can see here on the graph, if you go into this with no audit, then you only know what your current performance is, and you don't know what your actual maximum performance is. Maybe you have an idea of your expected future demand, but you don't know if it exceeds maximum performance because you don't know where that level is. And your potential performance, again, you don't actually know that. You just assume it's somewhere near the system limit. But that's kind of this fuzzy pink area on the graph. And so by having the performance audit and we establish what our current actual performance limit is, and looking at that in this graph, you see that the current performance is getting awfully close to that maximum performance. And so if anything perturbs it, then we're going to be out of capacity. And we see our expected future demand is already exceeding that. And when that happens, it won't actually be able to exceed that. So every workload is going to be slowed down to maintain within that maximum performance. Even though the system is capable of doing a lot more. The difference between that blue line and the green line is quite large. It's almost half the performance of the system. But without the right tuning to actually raise the maximum performance much closer to that green potential performance line, then that performance isn't available. So then we have the pitfalls of not having a performance audit. The first is the unanticipated impact, right? A change to an application, whether they release a new version of the application and it responds differently, or a workload changes, or a different season starts and suddenly a certain workload is much busier than it was before. If that's Black Friday and retail or whatever it might be. But as soon as that happens, what the current performance, which was good enough, suddenly our demand is higher and maybe it's not. And now everything's getting slowed down. And what are you going to do about it? And if you have an unanticipated impact because of a change of an application or something, and you thought you had more headroom than you really did, you get into problem number 2, the unbudgeted expansion. It's like our current demand is greater than our capacity. We need to solve this. We need more performance or more storage or both. And in doing that, having to do that right now without having planned ahead of time means it's outside your budget, and it's going to cause problems there. But also, as we talked about earlier, with the lead time on new hardware, what are you going to do for the weeks or even a couple of months before that hardware can actually arrive and be installed? You can't just not be able to keep up with your demand for weeks or months at a time. And so you can really end up in a pickle with that. Number 3 is, so the system has enough performance right now. What happens if a hard drive fails? Right? If you think back to the previous success story where they had 22 hard drives in their system, if one of those fails, you don't lose 1/22 of your performance, because now the remaining hard drives have to pick up the slack for the hard drive that's dead. And so you've reduced your overall performance by even more. And then when you're actually replacing the failed drive, there's that much more strain on all of the drives as they're having to read and reconstruct the data and write it to the replacement drive. And so during that, our current maximum performance comes way down. And if we don't have enough headroom to keep up, now we're not providing enough performance until that resilver operation is complete. So understanding how much headroom you have and how much you're going to have during a resilver is really important to making sure that you're able to meet the demand in all situations. And if you don't have an audit and you're trying to plan your expansion, but you know how much you're using right now, but you don't know how much the system can handle, and you don't have a great idea of how changes to the workload are going to impact it or how a resilver operation is going to impact it, how do you decide when and how much to grow your storage?
Right, so it's about a bit like being in the dark. So unless you measure your systems, you can't really improve your current performance because you don't know what the baseline is and what is the potential that you can reach. You can't really tell if you have any storage-related bottlenecks in your system. And you can't really prepare for storage failures, right? And as we've learned, health impacts performance in case of storage, and it's often forgotten. And for the future, you cannot really have an accurate growth estimation, right, without measuring your system first. So in a way, the storage performance impacts everything. And if you have slow storage, this can be a big issue. But on the other hand, since it impacts everything, it also gives you an opportunity to have system-wide performance gains. And the four main causes we look for during audits are the main four causes of storage performance methodologies are saturation, which happens when a specific resource is completely exhausted or consumed. We also look for amplification, which happens when your app is using a different block size than storage. And usually it results in storage doing more work than necessary. The opposite of an amplification is very often poor alignment, or maybe a similar issue related to blocks is poor alignment. It happens when your application is operating on offsets that are not the same offsets as your block storage things in. And as a result, whenever you write a block, it touches more than one block in storage, and then your storage, again, does more work than necessary. And the last cause is probably the most familiar one. This is the misconfiguration, which is basically that some part of the configuration of your system is suboptimal and is degrading performance. And the way we measure those is by looking at the metrics and collecting them. So let's take a look what metrics we focus on during an audit. So there are three main metrics we focus on. There is the throughput, which is probably the first metric people think of when they think about storage performance in general. And throughput is basically the bytes transferred per second. So even though it sounds easy, it is not as simple to interpret as people probably think. It is influenced by many other factors in your storage. But we'll get into that a bit later. Another metric we focus on are the IOPS. This is the IO operations per second. And then one of the interesting things about this metric is that for hard drives, for example, it's a limiting factor. And the biggest driver of IOPS is latency. So you can think about it as in a way that when you have a hard drive, it has to seek for your data, right, on the drive, but it can only do as many of those seek operations per second, and this influences the IOPS. So that's also a very important metric to look at. And the last one is the latency, which is the round trip time for an operation to complete.
Yeah, and these all put together are the building blocks of all performance. Like Matthias was saying, if a hard drive takes 4-point-something milliseconds on average for each seek, then in 1 second, which has 1,000 milliseconds in it, you can only do 1,000 divided by 4-point-something. You get about 250 IOPS. And outside of cases where two are right beside each other and can be aggregated into a single larger IOP, that's going to be the limiting factor.
Right, and then we have the deeper metrics. So once we understand the critical ones from the previous slide, we can take a look at those. So the first one we would like to tell you about is the average transaction size. So this is how big each IO is. And this is related to throughput. So throughput is average transaction size times IOPS. And the interesting thing is that, for example, if you're hitting IOPS limits, perhaps you can change the transaction size. For example, make it larger so that your IOPS are larger if you are exhausting them without having enough throughput. There are many ways to work with this metric. Another one is queue depth. So how many operations are waiting to complete. And this one is also interesting. So because it differs in how you think about it, depending on what hardware you have. So for hard drives, you usually can do one operation at a time. With SSDs, you can do a bit more, but not too many. But with NVMe's, you already have over 63 queues most of the time. So you can do much more work concurrently. And in those cases, perhaps you can make batching a bit less aggressive to get more performance out of the system. So taking a look at the queue depth helps a lot with that.
Yeah, like in general with hard drives, you want to keep the queue depth low because otherwise it drives up the latency, because the hard drive can only do one of those operations at a time. If you have a really deep queue depth, if you get a more important IO that comes in, it goes at the end of a long queue, it doesn't get serviced until that entire queue is done. Whereas with NVMe, because you have multiple queues and the latencies are so low that you have to try to keep those queues as full as possible to keep the drive busy enough to actually get the performance that it promises on the box.
Yeah, which brings us to the commit flash time, which is how long it takes to ensure data is safe on the disk. And it's important in case of flash-based storage devices, because very often they can only achieve their advertised IOPS with large queue depths. And this metric is related to that.
Yeah, and you need power loss protection on the SSD will allow these flushes to complete much more quickly because the cache on the drive will be protected. And so as soon as it's at least that far through the process, it can be acknowledged and you'll have a lower flush time. But if you don't have power loss protection, then each of those flushes is going to take longer and it's going to make a big difference on how many of these transactions you can do per second.
Yeah, and now by using all those metrics, we can optimize many systems, and we'd like to tell you one of the success stories of the work we did for one of our clients. So the system we were working on was had a ZFS pool made up of NVMe over Fabric devices, and the observed performance of the system was 2.1 gigabytes per second. However, the expected performance was 10 gigabytes per second. And when we were wondering why, what was the reason for this huge of a gap? So we took a look at the metrics and we discovered unusually high commit latency. And after some more digging and benchmarking and profiling, the resolution was to, apart from tuning the system, we also decided to modify the application itself, because it turned out there is a very simple way to make the application do less work, but still do the very same. We just optimized the way it uses the storage underneath. And as a result, we are able to achieve 8.3 gigabytes per second on this system, which it's a big performance gain.
Yeah, going from 2 gigs to 8 gigs definitely made people much happier.
Yeah. So in summary, the Clara Performance Audit solution evaluates the resiliency and performance of the system by analyzing key performance indicators such as resource utilization, infrastructure saturation, CPU profiling, and code inspection. So let's have a little recap of what we've covered so far. So in an audit, we first measure the performance of what we have. We measure the current performance, the current state of the system, what are the system's limits, basically what we have now, what we can work with, and how much room we still have to expand. Then we look at the expected performance, what is possible to achieve with the software we have and how we can tune and improve it. Basically, we want to understand if we can, how much performance we can get out of the system without adding additional hardware. And once we have it, we start to seek and apply improvements. And then the nice thing is that more often than ever, we discover those quick wins opportunities where a few small upgrades make a world of difference for the overall performance, as we saw in one of the mentioned success stories today.
Yeah, we're just adding 1% of the total storage is SSDs, made the system almost like it was completely a different system.
Yeah.
So now we'll talk a little bit about the process of ongoing auditing and why you need to be continuously vigilant to ensure success. So like we talked a bit about before, applications get updated, workloads shift, seasons change, events happen. So your storage, the demands on your storage are never going to stay exactly the same. And generally, they're just always going to go up as you're adding more and more applications or more data or whatever. And every one of those changes impacts your storage performance. Like we talked about before, adding a new application can increase the latency for every application. And if it's just by a little bit, then that's maybe okay. But at some point, it's going to start impacting things, and you need to understand how that's going to work and how it's happening and why it's happening and what you can do about it. So only by continuously auditing will you ensure that you have the ability to respond to these changes and make sure you know what you can do to ensure that these impacts don't impact your end users or customers. And it gives you the visibility that's the key to being able to plan and know, okay, on the current trend, we know we're going to need to add more performance at this point in the future. And we know, we're also going to need more storage at this other point in the future. How can we align those and make sure that we always have what we need? So the biggest parts of ongoing auditing are managing reliability, making sure that the data is staying safe and the system's operating properly, and that all the data is always available and ready to go. There's performance. We need to be able to note whenever performance changes, find out why it changed. Is there something we need to do about that? Does this change when we're going to need to grow? Are we going to run out of performance? Are we now at a point where the next time a disk fails, our overall performance is going to drop too much and we're going to need to do something about that? Then we continuously update our plans for growth. So we need to decide when we're going to need to grow and plan for that and budget for it and know, this is how we're going to respond when we reach these thresholds. Once our storage is 70% full, we're going to want to add, more storage, and we're going to have a plan in place for that and know what that looks like. And we want to manage the total cost of ownership. When it is time to grow, we want to spend the money where it's going to make the biggest difference. If we need more IOPS, but not more storage, then how we expand is going to be a lot different than our performance is fine. We have lots of headroom. We just need twice as much space now. And managing that and making sure that you're applying the budget to the items that are going to make the biggest difference. That's how you have success. So if you'd like to get started with that, please check out Clara's performance audits on our website. We have storage-specific audits as well as general system audits. Okay, our first question from Ihor. Do you have any optimization techniques that make sense in the cloud environment? For example, in AWS, EC2 VMs have EBS-backed disks that are not real hardware. Yes, a lot of the same things apply there. Again, the EBS disks that you're getting, Amazon advertises though as backed by hard drives or backed by SSDs, and the tuning for that can make a difference. But also because they're network attached, there's a higher latency floor there. And so the tuning you do will be a bit different because you want to make sure that you're queuing enough that you're making up for the latency it takes to talk to the network connected EBS disk and get the response back. But at the same time, not queuing so much that high priority IOs get stuck at the end of a long queue. Did you have anything else for that one, Matthews?
No, I think you've covered everything.
Okay. Next, I see Ruben has their hand up. If anybody else has any other questions, please type them into the question system, and we will work on answering those. In the meantime, if you'd like to get in touch with us, you can contact us via email, or we're on Twitter, or the contact form on our website. There's a question from Cedric. Oh, here's one from Mike. The success story where you added SSDs, was that NVMe or regular SSDs? That was just regular SAS SSDs. And even there, just, the IOPS you're getting there are tens of thousands versus, 200 per VDEV from hard drives. And it made a huge difference. The main reason they went with SSDs there was just that's what their existing system was all SAS based. And so adding a couple SSDs in their SAS chassis was the easiest approach, whereas the hardware, didn't have U2 slots or anything to add NVMe. Any other questions before we wrap up? Here's a great one for you, Matthews. They ask, what tools are you using to obtain the various metrics?
So usually we start with the standard tooling for ZFS, for example. So we look at IOStat, start to observe the system, how it looks like, how it behaves. If we want to observe the systems for a bit longer, we select Prometheus and node exporters. And then we gather metrics that give us a bit more of the understanding of what's happening on the system. And from there, we usually start to do some benchmarking to understand how the system reacts to different workloads. Yeah, and quite often once we identify where the bottlenecks are, we start to do profiling and tracing with various tools like perf or BPF trace to understand what's happening exactly and what's causing the bottleneck. And from there, if we can solve it with tuning, that's great. But very often it happens that we just hit some special case that is not yet covered by the existing code, and then we develop a patch that allows for improved performance for the special case of the customer.
Yep. And you also build Grafana dashboards out of the Prometheus data.
Oh yeah, of course, yeah. This is like a much nicer way to look at those metrics. Yeah, so Grafana dashboards are a big thing also.
Yep. Another question here. They ask, general question about Clara, have you worked with startups before? And if so, what kind of use cases have you helped them with? So one of the success stories we covered earlier was tuning the NVMe storage for a customer. That was a startup. We've also built custom ZFS features for startups. Being able to, you might have seen we upstreamed last year support for delegating ZFS datasets into Linux containers like LXD. That was for a startup. And basically whatever they need help with, whether it's just performance stuff. Another startup that we've helped, they were just evaluating which cloud provider would have the best performance for their workload with ZFS. They're providing API services to other startups. And in order to get the highest transaction rate, they need to know for our specific workload, which of these cloud provider provides the best, cost per gigabyte for storage that would give us the performance level we need. Deciding, is it Amazon or Google or Akamai that provides the sweet spot for performance for what their workload needed?
We also had some cases where we helped companies pick their NAS solutions, right?
Yeah. Another big thing we do for a number of customers is what we call ZFS design and implementation. So they've got some idea of what their needs are, but they'd like professional help designing the pool and picking out the hardware and then getting it actually deployed and in production. And part of that is, as part of deploying it, we make sure we understand what the actual expected performance is and getting that expected performance as close to the system limit as possible so they have that extra performance right from the beginning.
Yeah, and all of that with the future in mind, right? So that the system is expandable and fits their plans for growth in a way. It's always good to take into account.
Yep. Okay. Thanks everyone for attending, and we'll see you next time.
Thank you.